Okay guys, here we are on homework set 3 for OEH 5723. I'm going to go over problem N and hopefully we'll be able to get this solved in under 5 minutes because it tends to take me a long time. So we'll get to it. Okay, we first have a question that's asking us about the highest velocity at which a 100 micron particle can travel through air but still be in the Stokes region. Okay, so this problem is first going to make us ask, well, what does the Stokes region have to do with anything? So the Stokes region has to do with Reynolds number and viscosity and drag force and turbulence. So if we have a particle that's still in the Stokes region, then we know we have a lot of aerosol equations that can predict its behavior. Once we get into the transition region, it gets a little bit more difficult to calculate that Reynolds number. And then once we get into really high turbulence, we're actually getting into classic Newtonian particle motion. So we remember our definition of the Reynolds number as being the Reynolds number RE equals, let me pull it up so I don't write it wrong, the density, rho, the velocity, the relative velocity. So this is the density of air or the fluid, the relative velocity of the thing that's moving and the fluid, and then the diameter of the thing that's moving through, or really the diameter of the space of the gas that you're displacing, the fluid that you're displacing, and that is divided by the viscosity, which is nu. All right. So the constants to these are really easy to find. We've gone over them in class a number of times. But the tricky thing here is just remember that we're referencing air and not the particle density. So rho of air is, I believe, 1.2 kilograms per cubic meter. The diameter was given as 100 micrometers, which I usually just like to express as 100 and then times 10 to the minus 6 meters. And then our viscosity of air is 1.81 times 10 to the minus 5 kilograms per meter second. All right, kilograms per meter per second. So with those constants, we should be able to solve this really quite readily. So the other thing is we're basically saying what's the confine here. The confine is that we have a maximum Reynolds number, and that maximum Reynolds number is 1. So Reynolds number is 1. Can you guys still see that? Yeah. Okay. And then we just plug in and make sure that our units cancel. So 1.2 kilograms per cubic meter. Our velocity, I'm sorry, I'm getting all backwards here. We want to solve out for our velocity. So just need to rearrange this expression a little bit. So our velocity is going to be equal to Reynolds number times viscosity divided by, this has to come over, this has to come over, the density of air and the diameter that's being displaced. Okay, so now we can plug in and see what we get. So I'm just going to avoid erasing those. So our Reynolds number is set as being 1 because we're still in the Stokes region. And then our viscosity is 1.81 times 10 to the minus 5 kg per meter second. And then our density is 1.2 kilograms per cubic meter. And our diameter is 100 times 10 to the minus 6 meters. So we can see that this is going to cancel, and this will become a square. And then we can see that this will cancel and just leave us with meters. But of course that's meters in the denominator of the denominator. So this is going to be this meters. And then we have kilograms canceling. And we have seconds in the denominator of the numerator, which is right there. So meters per second. That's good. It's exactly what it should be. So now we punch out the numbers, and I actually worked this one ahead of time. So I have the numbers worked out, and what do I get? I get that it is 0.151. 0.151 meters per second. Alright, well, it wasn't less than 2 minutes. Sorry, sue me. It was, what, 5 minutes and, 6 minutes.